Hello everyone. Let's talk about sets. The picture you see on the screen is what we refer to as a Venn diagram. We shall make extensive use of this pictorial representation in our study of sets and their operations. First things first, however, we need a definition. What is a set? To me, a set is a collection of objects. Question, what is the difference between a set and all the other data types you have no doubt come across in your past studies? Let us first consider the difference between a set and a list. A set is much like a list, but without order and duplicates. By order, I mean a way in which I can determine what the first, second, or in general, nth element is. We will look at duplicates in a future slide. Sets are also like dictionaries, but without values, just keys. Let us look at an example. We have a set called mySet, which contains cat, dog, and horse as its elements. We may represent the set as a Venn diagram where the circle represents the set and the elements are enumerated within it. We now look at how one goes about creating a set in Python. First, declare a variable name and set it equal to the set function. This creates an empty set called mySet, which may be represented by the Venn diagram on your screen. We may also create a set from a list. First, create the list, then declare it equal to the set of myList. Coming back to duplicates from a couple of slides ago, notice how myList contains 2 copies of cat, but mySet contains only 1. I repeat once more, sets are oblivious to duplicates, as can be verified by asking Python to compute the length of mySet. All right, it is now time to look at some heavily used set operations. These are what sets apart from other data types and make it truly deserving of a place in the set of all data types. No pun intended there. The intersection of two sets returns all elements they have in common. We use the ampersand symbol to denote set intersection, as can be seen in this example. Please note how intersection is represented pictorially by the Venn diagram in the bottom right corner of your screen. We now turn to the union of two sets. The union of two sets is defined as the elements present in both the sets. For example, let water and mammal be two sets as defined. Their union, which is represented by the vertical bar, is given by whale, cat, dog, monkey, shark, tuna. Notice how the element whale appears only once. We now turn to subtraction. Since the definition is often a source of confusion, it may be helpful to turn to an example immediately. The difference of water and mammal, represented by the wonderfully original minus sign, is given by all the elements of the set water that do not appear in mammal. Again, please note the Venn diagram representation of the set difference. Finally, we turn to adding. As one might expect, we can also add an element to a set. Simply call the add function, which takes the element to be added as its argument. Now, an important fact that deserves our attention is that sets cannot be indexed. That is, type up water of 0 and you shall be greeted by the surprisingly concise error message, which says set object does not support indexing. However, sets can be looped over. Simply use the for loop as shown here to iterate over the elements of water. Notice that the same works for lists too. Surely, this is a much more readable syntax than what we're used to. Last but certainly not the least, we turn to the question of applicability. When should we use sets? Well, firstly, we use it to check whether something is in a collection or not. These checks are much faster than the same checks when done in lists. Secondly, we do it when there is a need for union, intersection, or subtraction. And finally, use sets when duplicates need to be get rid of. With this example, we come to an end of our discussion on sets and their operations. Now a puzzle for the inquisitive minds amongst you. Mainville is a town with one and only one barber. The barber shaves all those who do not shave themselves. The question is, who shaves the barber? This puzzle is a rendition of the famous paradox in set theory named after English philosopher and mathematician Bertrand Russell. Food for thought, people.